Welcome back to our course on industrial organization. Last week we finished our discussion of sophisticated price strategies of a monopolist. We looked into price discrimination, first degree price discrimination, second and third degree price discrimination. And we already started our discussion of product variety and product quality under monopoly. The question here was which products to offer, which quality should our products have, how many different varieties of a certain product are we going to offer, and if we sell several products, should we bundle them? What I already told you, or what I already gave you, is this example of these varieties. You can get the Head and Shoulders shampoo. And what you see here, it's really an interesting question. How many different varieties should we have of these, what economists call horizontally differentiated products? That is, this product caters to different consumers who are heterogeneous in the sense that they have different tastes or different needs in the sense of a dandruff shampoo. The other point, what we already had and what I already discussed at some length, is what is called vertical product differentiation here, with this different series of the BMW, where we have products which differ in qualities, and all consumers would say, yes, the 7 Series BMW is a higher quality than a 1 Series BMW. So that was what we already briefly discussed last week, where we started this discussion of what is called product differentiation, or one might also call this spread of horizontal product proliferation. Okay, if Kellogg's produces 25 different varieties of their cornflakes, or however they are called, this is product proliferation. Of course, it's always interesting to have pricing. What we already discussed was how many different varieties should we have, and if we produce different qualities, which qualities should we have. We will discuss product bundling only next week. That's why I skip it here at the moment. And what you will also see today, these kind of product varieties, they offer the model I present you offers a very interesting way to introduce price discrimination, even first degree price discrimination. Okay, so what I want to do first, what I want to start with, is to introduce you to a workhorse model of product differentiation, a so-called spatial approach, where we use what is called a spatial analogy. What we are looking here into is a model of horizontal product differentiation, where we have different consumers. In which respect do these consumers differ? Yeah, they are located at different distances from a shop. They live along a main street in a city, and they, in a sense, have a preferred shop. If you want to get on a Saturday morning your croissant, it's very nice if your bakery is next to your house and you don't have to travel for 3 kilometers because traveling is costly. And that's what we want to look into right now. It's a so-called spatial model, and it dates back to Harold Hotelling, who set this model up in a paper published in the Economic Journal in 1929. And what you will see, we can very nicely discuss product pricing in that respect. We can also discuss product design and product variety. In terms of pricing, an important question will be, do we want to serve all customers in our city or only part of them? In terms of design, we might discuss where to locate our shop. In terms of course, our shampoo, we might think about whether we should also have a dandruff shampoo for old men with gray hair, such as me. And in terms of variety, we might think about how many different shops to open, how many outlets of our bakery we should have in this city. And what is interesting here, or what is clear, of course, is if we have more varieties or if we have more shops, this saves traveling costs. And what is interesting, even though we put that here in spatial terms already, Hotelling wrote in his 29 paper that we can interpret this much more generally. And I just want to give you a quote from his 1929 original paper, where you will see that this location can be thought of course, as space, because that's how it is set up, but also in terms of times. Think of the departure times of planes, buses, and trains. So, of course, different departure times work differently or work in a different way for different customers who have different needs, and in terms of product characteristics. And Hotelling gave an interesting example or quote here, or interpretation here, and I quote him here literally: distance, as we have used it for illustration, is only a figurative term for a great congeries of qualities. Instead of sellers of an identical commodity separated geographically, we might have considered two competing cider merchants side by side, one selling a sweeter liquid than the other. If consumers of cider be thought of as varying by infinitesimal degrees in the sourness they desire, we have much the same situation as before. The measure of sourness now represents the distance, while instead of transportation costs, there are degrees of disutility resulting from the consumer getting cider more or less different from what he wants. So what we have here already is what Hotelling called disutility. There's something missing here. Disutility. Okay, so you don't get the real exact design of what you would like most, and then you have some disutility cost, which might be modeled here as these transport costs. And again, it was already mentioned, this infinitesimal, so there are just very many consumers which differ only or where you have a rather densely populated product range in a sense. And that's what I want to show you next. How do we model this? We just assume that there are capital N consumers living equally spaced along a main street. And this main street is, for simplicity, just 1 kilometer long. Suppose it's 1 million consumers will live along 1 kilometer. You might also, then of course, the density of these consumers, or the measure of consumers, the density of consumers would be 1 million here in this 1 kilometer. If it's 10 kilometers, it would be just the density 100,000 per kilometer. Okay, we can easily do that. It's just a difference whether we have 1-story houses, 2-story houses, or skyscrapers with 100 floors. Okay, so this n is given that it's a continuum of consumers. It might also be called a measure of the number of consumers, but simply just take it as 1 million or something like that. And what we assume next, and you will see where on the next slide how we draw this. And what we have to do next is we have to look into the monopolist decision problem. He needs to decide, or she needs to decide, how best to supply these consumers. And what we assume that it is how many stores to open, for instance. And we assume that consumers have what is called unit demand. So they buy exactly 1 unit, provided that the price, inclusive of the transport cost, is less than their maximum willingness to pay, or their reservation price, which is called V here. And in terms of the transport costs, we assume that these are T per unit, and these are there and back. So of course, if you go to the bakery, you have to go there and you have to go back, but we just assume that this T covers everything. And once we have this assumption, the indirect utility of consumer I located at Xi and buying at a shop located at X lower bar, which charges a price. P is simply this here. So we have the utility of our consumer I. It's an indirect utility because it already takes account of the price. This consumer is supposed to have a reservation price. We assume that all consumers have the same reservation price, and here we have the distance from the store. If you're located at some place Xi, or some location Xi, and the distance or the shop is located at X lower bar, only what matters is the difference. Therefore, we use these absolute signs here. Okay, and yeah, that's how it is. So reservation price minus what we have here, price plus transportation cost. And suppose the monopolist just operates one shop, then of course it's clear if it operates only one shop, it will operate it in the center of the main street, because otherwise we wouldn't minimize the maximum transportation cost. It's obvious. The question is then what would be the optimal price, and that's what we look into right now, and that's where you finally see our nice linear city. Okay, this is our linear city where we have here a shop or consumers located along this line here. This is with 1 kilometer. One consumer is located at 0, the other is 1, and we have a densely populated street where a density N, capital N, of consumers live. So again, if it's 1 kilometer and we have 10,000 people living in that, the density would be 10,000 here because it's 1 kilometer long. At 1/2 is our shop located, and now this V, of course, on the vertical axis or on the y-axis, we depict the price, and of course then the maximum price the people or the consumers are willing to pay is this V, which is the same for all. And now suppose that the monopolist sets a price of P1. So this is our P1 here. So this would be P1, okay? And so what is this T here? Of course here, what we know from up there is that, oh, I have to erase that, all consumers within the distance x1 to the left and to the right of the shop will buy the product. Why? Because, and that's what's written here, because if they are at the distance x1 here, okay, their transport cost will be T times x1, and T is just the slope here of this line, and therefore this is just our Tx1. And given we have a P1 plus this Tx1, this is just the pivotal or the indifferent consumer located here at this distance x1 from the shop. And here, of course, it doesn't matter whether I go to the left from the center or that was the right, but or to the left of the shop. It's always the same. So everyone within the distance from x1, all these guys here will buy from the shop. The others won't buy at these prices because, as you see here, their price of this guy here, for instance, the price inclusive the transport cost is above her willingness to pay. Okay, that's what we have here, and so we can immediately write down how x1 is determined by just manipulating that and rearranging, so we get v minus p1 over t. Okay, and the next question is, suppose the firm reduces the price, what happens? Yeah, it's clear we now get all the consumers who are located at a distance of x2 from the shop. If we want to serve everyone in the market, of course, now that's not written down here, you would get something like this here. Oh, that was the second line was rather poorly drawn, something like this. At this price, everyone would buy. And what is clear already, and what you should always have in mind, it never makes sense to reduce the price below this price here, because that would just mean you don't get any additional consumers, but you give these consumers here a rent. All other consumers get a rent anyway, and that's something which you will try to reduce by adding further shops. Okay, so what we have here, if we want to serve everyone here, and that's what I just depicted, the highest price is then the price so that consumers at the end of the markets just buy. They are located at a distance of 1/2 kilometer, so their transport costs are T over 2 as they travel 1/2 kilometer, and so their price inclusive transport cost is P plus T over 2. And of course, that must not be greater than V, otherwise they don't buy. So the maximum price you can charge, and that was exactly what I just showed you, so that everyone buys, is P equal to V minus T over 2. And then suppose that we have some marginal cost C per unit, and suppose that we have some fixed costs, some setup costs, some rental costs, and all this of F. Then the profit, if you have a number of consumers which is equal to capital N, if you operate one shop, is simply here the number of consumers, because that's equal to the demand. And this V minus T over 2 is nothing else than the price minus cost minus variable cost. So this is the whole expression here in brackets is the profit per unit minus the fixed cost. Okay, that's our basic setup. Hopefully this was clear. Then of course the question is, what would happen if we add another shop? If we add another shop, the monopolist, of course, will coordinate prices at the two shops. So that means simply that she will charge the same price in both shops. And if the costs are identical, we certainly will also see symmetric locations. And these prices will also be equal. The question is, of course, there are many symmetric locations. Both could be located at the center. Both could be located at the edges, one at 0 and one at 1. And all many different symmetric locations as well. So the question is, where should they be located, and what is then the optimal price? Typically, you solve such a problem in a recursive way. That is, you start with given locations, look what then the optimal price is, and then you optimize or look into what the optimal locations are given this pricing rule in the next step, in a sense. Okay, that's what we are looking into right now. So if we have two shops, so if there are any questions, just ask them in WebEx. If there are two shops, and if we assume that we want to serve the entire market, okay, again, they will be located symmetrically, and suppose for a minute that they are located at a distance d from the endpoints of the market, and suppose that this distance d is smaller than 1/4. So about here is 1/4, and here actually in the end you will see that the optimal thing is to locate them at 1/4, but we have to of course prove that. And if they are located at d here, which is the distance from the edges is less than 1/4. That's what we had here. And we start with some low price. Of course, this is not an optimal price, because even this guy who has the highest price, inclusive the transport costs, this guy at the center, this pivotal consumer, she has a rather high consumer surplus. Therefore, we will increase the price until this guy is just indifferent between buying and not buying. Okay, and this is some maximum price. Okay, and what we see here already here is that we leave a lot of surplus to these other guys at 0 and 1. Okay, and you already get an idea that it might not be a good thing. Of course, we determined here PD. Okay, what is then the optimal price you can charge if you want to serve everyone, and if you're located at a distance d from the endpoints? Okay, how do we determine that? That's the content of the next slide. What you already can see here, what might give you an idea is that if we move closer to the center, we reduce this consumer surplus up here from the people at the edges, and therefore can at the same time increase the price for the consumer here at the center without losing this consumer. So what happens if we have a d smaller than 1/4? We know that this PD satisfies the following constraint. Remember that the pivotal consumer, that the indifferent consumer, was the one located at the center. Okay, and her transport cost or her distance was simply this 1/2 minus the d, because the d was the distance of the shop from the edge. Okay, if d would be 0, it would be 1/2, because then the shops would have been located at 0 and at 1. If it's 1/4, it would be 1/4. If it's 1/10, it would be just 1/2 minus 1/10. And so that's how we determine the price. If we solve this for P, just rearrange it here, we know that if we want to be located at D, the maximum price we can charge so that everyone is served in a market is just this V minus T over 2 plus T times D. And what is the aggregate profit then? The aggregate profit is just this P minus C times the aggregate consumption. The P is nothing else than V minus T over 2 plus TD minus C. And what we see here is, if we take the derivative or if we just increase the D, we see if we increase the D, our profit will increase. So that's already the formal proof for the fact that it's not optimal to have a D smaller than 1/4. Remember, our definition holds only or is relevant only for D smaller or say equal to 1/4. If we have a D chosen which is smaller than 1/4, our profit would increase if we increase D. Okay? Should be clear and is already clear from the diagram. Same thing or analogous thing if we suppose that we are located at D greater than 1/4. Again, sometime I should add here this 1/4. Okay, it's about here then. And now, who is now the pivotal consumer? Actually, it's now the consumers at the endpoints because they are farther away from the shops than this guy in the center. And of course, now again, we can raise the price, and the maximum price is just the one, so that these guys just are indifferent between buying and not buying. And what we see here, not a good idea. We leave a lot of consumer surplus here to the consumer located in the center. Okay? And again, we get some PD here, again, our price. Again, the question is, what determines PD? That's what we are going to do on the next slide. And again, what we see already here is if we move outside, if we move up here, for instance, we could increase our price here, okay? And that's what we show in the next slide. This is straightforward, just the same problem. Now the point is that now the distance is D because remember our pivotal consumers here are located at the edges at 0 and 1. So the distance to the shop is exactly this distance D, holds both for the guy at the left-hand side and at the right end of the market. So this is simply D. And same problem, our price is then just V minus TD. Aggregate profit is then similarly this price minus the cost. And now what you see immediately, if we increase D, we have a negative sign here, or if we take a derivative with respect to D, this derivative is negative, so it's optimal to reduce D. And so this is decreasing in D, so D should be decreased. And then we can write down both cases. And the case here written down here, if D is greater than 1/4 is this here. If D is smaller than 1/4, this was 2 slides ago. It's this expression, and actually the two expressions, the two terms are identical if D is equal to 1/4. So this is this profit as a function of the distance D is continuous, but it's not differentiable because it has a positive slope if we are to the left of 1/4 and a negative slope if we are to the right of 1/4. So the optimal thing is to have D equal 1/4. That's what we now also formally prove. Okay, and for whatever reason here, I have these bubbles here without the text, but what you see here already, our 1/4 and 3/4, our optimal shops, and what we see is here, what is the maximum distance our consumers here have to travel? It's 1/4 then, of course. What we did is we minimized the maximum distance. And what you see here is both these guys on the edges, on the endpoints, and the guy located in the center, they don't get any consumer surplus. Okay, that's what we have here. And this is what is the optimal price here, this V minus T over 4. Okay, and the profit at each shop is given by the shaded area. And the profit in this case, where we have two firms, is in terms of the operating profits higher than before. Remember, before we had a price of V minus T over 2 rather than, and T over 2 of course is T over 2 of course is greater than T over 4. Therefore we subtract more, and therefore the price was lower we had once we used only one shop. Okay, so the point is our operating profit increases, but at the same time, of course, we have more fixed costs to pay because we have two outlets. Okay. And now, of course, what happens if there are three shops? If there are three shops, of course, what we already know where we will locate the shops not at 1/4, but at 1/6, at 3/6, and at 5/6. Okay, because what you see immediately again, this minimizes the transport costs, and we get the new price is again higher. Okay, we subtract even less. The new price is higher, and we get a higher operating profit, but of course at the same time have to pay higher transport costs. Okay, rather straightforward, higher operating profit. And now that's what Pepperidge's Norman state, a consistent pattern emerges. Assume we have n shops right now. Of course, they will be symmetrically located at a distance of 1n from each other. And we start at 1 over 2n. And the maximum distance a consumer has to travel is 1 over 2n. Remember, in the case of 3 shops, it was 1 over 6. Okay, and the optimum locations, that's what I already told you. And that was 1/6, 3/6, and 5/6 in this case. So that's what we already had. Here you see that how prices evolve. And of course, if you have infinitely many shops, that's interesting. This 6, you would have an infinity here, and actually you would have it here. If n approaches infinity, you would just charge a price equal to the reservation price, okay? And of course, it's clear you will never have infinitely many shops because we have the fixed cost. But what you can write down is the aggregate profit as a number of shops. Again, it's always the same number of consumers. That's the same number of units sold. The price depends on the number of shops. Of course, we always have to subtract variable cost, and here we get here n times the fixed cost. Okay, and then what we are doing is ask how many shops should there be. Yeah, and given this just reproduces what I just wrote, the question is, what happens if I add another shop? If I add another shop, of course, my price changes. That's exactly what's happening here. If I add another shop, and under what circumstance do I add another shop? If the profit, if I add another shop, is higher than, so if I have n+1 shops, is higher than if I have n shops. What is very important here, it's not that this profit is positive or this profit. That will most certainly be the case. The question is whether I add, not that our single shop breaks even, but whether the total profit increases, because of course the profit of the n+1 shop will at some part come from these n previous shops. Okay, so we will see what economists call cannibalization. We will see some cannibalization. And the question is, so how many shops should we add? And therefore, we just calculate the maximum number of n for which this is satisfied. If we substitute that here in these two conditions up here, in these two profit functions, you just see and rearrange that. You will see you can rearrange to get this expression. And this is, by the way, a expression which can nicely be interpreted, because here you have the additional fixed cost you have if you have an additional shop, and this additional costs must be smaller in a sense than your additional revenue accruing from the price increase you get. Okay, you can increase the price, and so this is the benefits from the additional product variety. That's what's behind this expression here. Okay, and so what we get if we rearrange that, we get an expression in terms of n times n plus 1 must be smaller than this expression t times n over 2f. In order to make clearer what that is, I just give you an example here. Suppose some numerical example. Suppose you have some fixed cost f of 50,000, some 5 million population, and transport cost of $1 per kilometer. Then you immediately get an expression for this term here, or a value for this term. This is simply 50. And so what we need to get is, we know that adding another outlet is optimal if this is just smaller than 50, and this gives you just 6, because 6 times 7 is 42. 7 times 8 would be 56. So if you have 6 shops, it's optimal to add another one. If you have 7, it's no longer optimal to add one. So that's exactly what's adding here, or what's written here, and of course, you can just write that down, and you will see that then your profit goes down. That, of course, should read pi rather than p here. Okay, and this requires exactly this to be the case. Does this make sense? What does this condition tell us? Of course, it tells us we find a greater product variety if we have many or more consumers, if this capital N is larger. Should be clear, because then you just have more and more economies of scale in a sense. Okay, so in that respect, these setup costs are not so important. Of course, they are not so important as well if the costs are low. So under what circumstance will we have many shampoos? Yeah, if adding an additional shampoo variety is very cheap, that can be because you just put the same shampoo in and just put a different label on your pack, okay, on this, what is Flasche, okay, on your bottle, okay, and of course if you have many different consumers, and it's also if this parameter t is small. If it's large, because that also relaxes this condition. If it's large, consumers have strong preferences over product characteristics and differ in these. Okay, if I with my gray hair know this other shampoo is a dandruff shampoo, but you have to have blonde hair so that it works well, then I don't buy this other thing. Okay, and if you have very strong preferences, you will see you have many varieties. Actually, this parameter t is very important in marketing because you always want to have that you have very loyal consumers, and you want to have consumers which have a high transport costs. Okay, because that allows you to charge a high price in a sense. Okay. I think I make a short break here and ask for questions, and before I move on to ask how or whether we want to serve all our customers anyway. How much of the market to supply? So previously we assumed that that our monopolist wants to serve the whole market, wants to serve every customer. And that's a question whether we actually want to do that. And the question is then, of course, if we don't want to do that, suppose not, then each shop has a local monopoly in the sense that each shop sells consumers within a distance R, and in a sense there are holes in the city of consumers who are not served. And how is this R determined? Of course, again, this is a maximum willingness to pay, or the reservation price, and the price inclusive of the transport cost must just be equal to that, so that our consumer is indifferent between buying and not buying, and this immediately determines our R, our distance from the shop, so that our consumers still buy. Okay, rearranging is just that R is equal to V minus P over T. And of course, you have these customers to the left and to the right of your shop. That's why you get a 2 here. And of course, you have to multiply it with the capital N, the density, how many consumers live there in this region R. Okay, and then the profit to each shop is simply this pi. Here's the number of, or the density of consumers here. That's actually here this price. That's okay. Probably I should start from here, and this 2n, and here's just p minus c. So just I probably could put it nicer, but it should be clear this is just quantity, which is now no longer the total quantity of the market, or just 1/n of the market, which each shop gets, but just the consumers within this range R. Okay, and now what we can do here, now we simply get a demand which depends on the price. And if demand depends on the price, we can just look how does profit change if we increase or if we change the price, and that's how we do it. Typically, we just take a derivative with respect to P in this case and set the resulting first order condition equal to 0. We get this here, and we can solve for the optimal price. And remember, this is just the standard monopoly price. So this is V is just the maximum willingness to pay, and this or it would be a vertical intercept if we have a linear demand curve. So it's just A plus C over 2 standard monopoly price, which we get here. Now the question is, under what circumstance will we charge just such a monopoly price, or will we charge a price so that we serve everyone? So if we want to serve all consumers, the price P, capital N, number of consumers, small n number of outlets, would be just this. That's what we just determined. And now note, if P star, this monopoly price, is equal to that, we would just cover everyone. Okay, so our price, from if parameters are such that this holds, we would just have a corner solution, in a sense that with the monopoly price, our R would be just equal to this 1 over 2n, to this distance. If we then were to increase the price, if we were were to decrease this price P star, of course, that would be a bad thing, because if we would never attract additional consumers, because we serve everyone anyway. Okay, so if this monopoly price is lower than this price here, it would not be a good idea to reduce the price below this price in which everyone is served, because we don't attract additional consumers. Only in the case in which the monopoly price is higher than this price, it would be a good idea, because then it would be good to reduce the number of consumers we serve. And that should become clear in a minute here. Increasing the price will increase the profit. In this case, it's better not to serve the whole market. We can look into that in even more formal terms by, it's exactly the same first order condition, by evaluating this derivative at the price which we get in the case in which all consumers are served. That's what we are doing here. So here is our first order condition, and for this price here, we just substitute the price we have if everyone is served. And now this first order condition evaluated here, if that's greater than this at this price, it's optimal to increase the price. If it's smaller, it's not good, okay? And here in the next line, I just simplified that or put that in other terms. So increasing P above these price where we serve everyone is only optimal if the slope, or if the sign of this derivative is positive. And this holds only if V is smaller than, so this greater relates to this smaller if V is smaller than C plus T over N, or on the other hand, if C is very high, it's better to increase the price above this price where you serve everyone and only you serve only the market. In case you printed out or downloaded the slide deck, I added just this single line here, okay? Hopefully it's clear. If it's not clear, it's always better to illustrate it in terms of a diagram. Okay, so here suppose or we know that if we have two shops, as we have in this case, the price will be V minus T over 4. And suppose this is our cost, then we would know that V plus C over 2, which would be about here, would be our monopoly price. If we charge this monopoly price, it's clear it doesn't make sense to reduce to reduce this price below the price we have here, because by reducing this price to this monopoly price, we would just give a consumer surplus to the guys here at the edges as well. And the monopoly this monopoly problem, or this first order condition, implicitly assumes that we would attract additional consumers also here. But of course, that doesn't matter, or that cannot happen, because there are no additional consumers. So if we have low marginal cost, it's a good thing to serve everyone, because here in this case, the monopoly price, our P star from the previous slide, would be below this price if we serve everyone. This is different if we have, for instance, very high marginal costs, such as here, because if we have this very high marginal cost, you see your profit would be only this here, okay? That you serve everyone, but you get only a very little profit here in this respect. If you, on the other hand, introduce a monopoly price, this would be, you would no longer serve everyone. And I think you would something like, this would be your price, so you would serve only up to, again, this is not really, you would serve only up to here, but again, then this part here would probably be larger than the other. Probably I should use a different color. And it would look different than what we previously had. Okay, we get, use a different color here. Of course, it's not perfect, but here what you see is you would get this, if we draw this in terms of 2. My drawings are not very nice, but you see this is probably larger than what we originally had, this area here between CH and V minus T over 4. Okay, here you see here it's really clear because your monopoly price is higher. And I erase it again, otherwise you won't recognize anything anymore. Because your monopoly price is now above your monopoly price P star is above the price in which you serve everyone. Okay? What I draw here is just the case in which this P star and this monopoly price and the price in which you serve everyone, in which this coincides. You just solve this for C and you get then V minus T over 2, because then you see your monopoly price will be just V plus C, or will just be equal to V minus T over 2. Okay? So the point here, what I want to show you, and that's what I show you also in the notes, if you have C equal to V minus T over 2, this is exactly the cost level at which this P star, the monopoly price, which is then, by no coincidence, equal to V minus 2 over T over 4, coincides with the price in which you serve everyone. And given you have this marginal cost, for all marginal cost levels above this V minus T over 2, it's optimal to serve only part of the market. For all cost levels below, it's optimal to serve everyone. Okay, that's what you have. And that's exactly what's stated here. Okay, and that's what we have here. And here we have the interpretation. If the consumer reservation price is low relative to the marginal production cost, it's good to serve only part of the market, because that's what you see here. If V is not here but up here, it's never, you will always want to serve everyone. And on the other hand, what we already showed, if C is very high here, if the marginal costs are very high, it's also more likely that you don't want to serve everyone. Okay, and of course, what you see here is the price, of course, increases you charge if you serve everyone if you have more outlets. So, of course, one idea or one way to serve the whole market is to add additional outlets. So why should you not just add shops? The problem is here you have an integer problem. You have the fixed cost. If the fixed costs are high, and then it just might be a problem. Okay, it might be good to add just a half a shop, but you have to add always full shop. Okay, so that's what we have. Yeah. Now we looked into the decision of the monopolist. First of all, this determining what the monopolist's optimal number of outlets is, and under what circumstance we will serve the whole market. Now we look into the social planner's decision problem, or what we actually want to do, whether Procter & Gamble has too many different varieties of shampoos or not. Okay, as you might guess, it's too many. Okay, and that's what we are going to show, at least if we believe in the Hotelling-Modell. So what we want to do is to look into to determine what number of shops maximizes total surplus. And what is total surplus? Total surplus is simply consumer surplus plus profit. Consumer surplus is total willingness to pay. This is just the V minus the total revenue. Profit is total revenue minus total cost. So as this total revenue just shows up both in a consumer surplus and in a profit, total surplus is just total willingness to pay minus total cost. Total willingness to pay of the consumers is just each consumer has a willingness to pay of V. We have capital N consumers, so total willingness to pay is N times V, and this is nothing else than in our diagram here, the whole area, okay, below V times N. Okay, that's what we have here. And what is total cost? Total cost for the social planner, if there are N shops, of course, we have N times the fixed cost. And what are the transport costs? Okay, setup cost is clear, n times the fixed cost, but what are the transport costs we have? So this is also a cost in terms of our social planner. And what we see here is if we have n shops, each shop will serve 1 over n consumers, and therefore the maximum distance of a consumer, or actually the total transport costs, will be just these two red triangles, okay? Because this guy here with the maximum distance has this transport cost, and all others just accordingly. The guy located where the shop located is, the consumer, has just transport cost of 0, and it's straightforward to calculate the area of these triangles. Here we have just 1 over 2n times t over 2n, and then over 2, but as we have to get the area of one of these triangles, but as we have 2, we get rid of this division by 2. So this total red area is simply t over 4n squared. Okay? But once we have this, we know our total cost is simply, if we have capital N, of course, because that determines our output, this is just our transport cost, n times this t over 4. So this was these two red triangles. We have n of these triangles because we have n of these shops, and we have, of course, a density capital N plus n times the fixed cost. And what we want to do, and that's how we can write it then, and that's what we do. What we want to do is we want to minimize total cost. Okay, that's the only thing we are interested in, because we know n times v is given anyway and constant. So under what circumstance is it optimal to add another shop? If the total costs with n plus 1 shops are lower than if we have n shops. That's what we are doing. And we proceed as we did above. Okay, again, we just substitute these expressions here, and we get something like this here, and manipulating, so we get a similar term as previously here, and the condition on a small n on the number of outlets here. We can immediately see that this expression is just half of the expression we have here. Okay, of the condition of the monopolist. So remember, above it was 50, now it's just 25, and that means we have a more restrictive condition on n, and we get therefore a lower number of firms which a social planner would choose. And therefore we get this result: the monopolist operates too many shops, and more generally provides too much product variety, too much shampoo, too many different varieties of shampoos. Okay, that's what we get here. And on the next slide, it's just for our example, where we would see that the social planner would only operate as n equal 4 satisfies this condition, and it's optimal to add another shop. It would only operate 5 shops rather than the 7 we saw from the monopolist. So the monopolist operates too many shops here. Okay, that's what we get here. Why is that so? Probably we should, and I think I explained that here on the other slide or in the notes. Why is that so? Why do we get this result? Now, under what circumstance does the social planner operate an additional shop? If it reduces the total cost. Under what circumstance will the monopolist open up an additional shop? If it increases its profit. How can the social planner increase its profit? Now, if it adds another shop, it is able to charge a higher price. Okay, and therefore it redistributes some consumer surplus to the firm and turns it into profit. Okay, and this redistribution, this is just something the social planner doesn't care of or doesn't care for. And that's why we get too much variety here. The firm adds too many shops, as this will turn consumer surplus into profit, and therefore it overinvests in a sense in fixed costs. from a social point of view, because it even adds a shop, even though that does not reduce the total cost. It just increases its profit by enabling it to increase its price and therefore to attract or extract more consumer surplus. Okay, that's what we have here. What is very interesting in that respect, there is a fabulous strategy in order to implement a first-degree price discrimination in this setup, in this model. And how does that work? Suppose your monopolist delivers the product. So the consumers no longer have to go to the shop, but they get freely delivered the product. Okay? Then the firm is able to price discriminate. Why? What can it do? It just can charge the reservation price V from each consumer. And the firm simply pays the transportation cost. What does this mean? Everyone gets the same delivered price. Okay, preisfrei Haus in a sense, so free on board. So this would be a uniform delivered price. Everyone pays the V. Okay, but of course this would be discriminatory, because if you're located at the edge of the market, you have to pay the same as if you're located exactly at the position of a firm. Okay. And therefore, you really perfectly price discriminate, because you extract all consumer surplus. First-degree price discrimination. The question is, would you want to supply all the consumers? Yeah, suppose you have, again, N shops. The cost to the most distant consumer is then, if you have N shops, it's just 1/2N is the distance. Therefore, your cost will be, of course, the production cost plus your delivery cost. And what you're doing is you supply this consumer as long as the revenue, the V you charge, is higher than these production costs plus the transport cost. And this, of course, is a weaker condition than without price discrimination. Remember that there it was this C/2 plus 2/N. That's what I derived some slides ago. Okay, and that means that price discrimination allows more consumers to be served, and that's similar to what we had above. Of course, under a perfect price discrimination, under first-degree price discrimination, under personalized pricing, you have an efficient output. Everyone who is willing to pay at least the cost he or she causes will receive the product. Okay. And the question is then, how many shops should the monopolist operate now? And suppose the monopolist has N shops and is supplying the entire market, then total revenue minus production cost is just a given thing. You serve everyone, so this is just given. And the total transport cost plus the setup cost is just, remember, this was the Tn/4n plus the Nf. This is exactly the same as what the monopolist had, because you just cover what the monopolist what the social planner covered. And so your profit is simply this here. And what you want to do, as these are constants here, n times v minus n times c, you simply minimize this total cost, and this is exactly what the social planner did. So the discriminating monopolists operates a socially optimal number of shops. Okay, again we have perfect price discrimination. And here you see, you even are able to increase your profit. I just want to highlight this by means of our, this is a bad example because I put too many, hopefully this is better. I put too many sketches in there. So here what you do is actually you just charge a price equal V, and then you cover this transport cost here. Okay? You cover this transport cost. And so what you get in terms from this guy here, you deliver it free on board, okay? But you get the whole price here. And of course, from this guy, you extract this here again. And so from everyone, you extract everything. The only thing is, of course, this guy here gives you, and that's gives you slightly lower surplus, slightly lower profit. Okay, so in a sense, we could the profit given this here, the profit per consumer from this consumer, you would get this here, and this is a maximum consumer. From this consumer, you would have to pay these transport costs, so the profit would simply be this I don't know, it's a trapezoid, this area. Okay, so it's really a good idea to do that. So what should MediaMarkt do, and all these firms? They should just freely deliver it to you. Okay, or your bakery, what should they do? They should just provide services that they deliver your morning croissant, because then they could price discriminate. Okay, so we should just think about that. So that was what I just showed you. So what we had here was a rather clear-cut result in terms of whether we have too much or too little variety. And it's rather, in a sense, it's peculiar, because what we didn't have here was an efficiency problem. Because at least in a case where everyone was served, we had unit demand and everyone was served. So there was no problem whether the price is high or low. Demand was always just one from everyone. But typically, we also have a price elastic demand. So depending on the price of the product, you buy 1, 2, 3, or 4 units. And what I want to show you is a slightly different model of horizontal product differentiation. And I don't know whether we already introduced this so-called linear quadratic utility function here, or the Bowley function, done already by Sig-Weaves in the 78s or so, where you have these differentiated products. You have this utility function, and if you have some numeraire good which enters linearly, you get equal simply that Pi here, the inverse demand would be simply Ai minus Bxi minus S, and then sum of all j which are different from I from xj here. Okay, this would simply, and if you have only two products here, this would be just x2 here, if we look into product 1. So this is a rather straightforward and simple linear quadratic utility function, which I use in all my courses. And the interesting thing is, of course, this gives rise to this very straightforward inverse demand function. The demand function itself looks a bit more complicated. The complication comes from the S, from the substitution parameter, because if all firms, or if the products, the different varieties, are homogeneous, this S would be equal to 1, and we get a 0 in the denominator. And this makes only sense if I sell everything at all varieties at the same price. Then it's well defined, your demand for each function. Anyway, so this is just a demand function which exhibits so-called love of variety. So now we have a consumer whose demand is depending on the price. Of course, if the price is lower, we get a higher demand. And where consumers also consume different varieties. Think in terms of songs. Even though songs is a bad example, but in terms of, say, the restaurant visits you make, you typically will not always visit the same restaurant. Okay, you might visit to one different restaurants, whereas in this hotelling model you only have neighboring products. Here you have different products. Okay. Here it's not so clear that Italian food is the direct neighbor of say Mexican food, and the direct neighbor of Turkish food, whereas if you have two bakeries which are along a high street or a main street, it's clear which one is nearer to the other. Okay. Naja, if you have this here, you just can write down the profit function. Here again, what we previously had, you have the number of varieties n, you have some fixed cost f here. And again, I like to change to the red color here. And some fixed cost, and here you get the profit per unit, and here this is just your demand function. The whole thing here is the demand function here. And what you do here, or what I did here, is I just first looked for the optimal price. Actually, the optimal price is a simple monopoly price, A plus C over 2, which you charge for all varieties. And the outcome is, if you look into the problem of a second best planner, second best social planner, you get the opposite result as previously. Second best social planner is here, what I mean by a second best social planner is simply that the second best social planner accepts the monopoly pricing of the firm. So given that we assume that the pricing of each variety is that price is A plus C over 2 for each variety, you see here, this is social planner, and the red thing is the monopolist. You see, if you, for instance, have this substitution or differentiation parameter is 0.4, then it's clear that the monopolist will produce, say, about 70 or it's about 12 units, and the social planner would choose 5 more. Okay, so here you get the opposite result. Here you get the result that the monopolist underinvests in product variety. Why is this so? It's due to the people who took the Economics of Innovation course will be familiar with that. It's due to the so-called consumer surplus effect. Despite the monopoly pricing, if the monopolist adds another variety, okay, if it adds another variety, of course, it earns some monopoly profit, but at the same time, each consumer, in a sense, gets a small consumer surplus triangle from this. And of course, the monopolist does not take this consumer surplus into account, which is produced here. Okay, the important point is here, if we add another variety, the price is unchanged. Why would the monopolist add another variety then at all? Because that increases aggregate demand. Okay, it increases aggregate demand. But of course, this effect is not as strong as it is for the social planner, because you just sell a few more units, you get another monopoly surplus or monopoly profit, but you cannot extract the consumer surplus. That's why you get under provision here. So you see, it really depends on what you have and in which world you are, whether you have an under or an over provision of product variety by a monopolist. So it's rather complicated. So if your setup, if your world is more like hotelling with these neighboring products, that's rather clear that if you have such ideal varieties, it's more that you get the over provision of variety. If you have this love of variety, we more or less get under provision of variety. Okay, I ask for a question right now, and then I would briefly start our discussion of monopoly and product quality. So we move on to vertical product differentiation. However, we start here with the case of a single product where the firm or our monopolist decides on which quality to offer. Okay, after we had some very interesting discussions about whether we should deliver as a monopolist to our customers, or whether we should pay some student to deliver it if we know the exact distance, that's really interesting, because if the transport costs for delivery are cheaper than the transport costs if the professor on his own gets to fetch his morning croissant, That would be interesting, because price discrimination would work in both cases, but the profit would be higher if I can deliver at lower cost. Okay, so we now start with this discussion of product quality. So for the moment, we only focus on the question if our monopolist produces a single product and can choose the quality of the product. So quality, of course, is an important strategic variable, and of course, a monopolist determines the quality in order to maximize or to generate profit. For the moment, we focus on the single good case, and the question is then, which quality should it have? And of course, which quality it should have, this decision is determined by the consumer's attitudes to quality. And so what we typically assume is that our consumers prefer high to low quality and therefore are willing to pay more for high quality. But of course, the question is, we really need to recognize, to be able to recognize quality. We need to be able to tell that it's a higher quality. And of course, consumers might be heterogeneous in terms of their willingness to pay for quality. Typically, we will assume that the rich ones, people which have higher incomes, are willing to pay more for a higher quality than people who are poorer. At least that's a standard kind of assumption. So suppose we have different individuals. Again, we have very many. We have a continuum, and again assume that we have unit demand. So our consumer consumes 1 unit if the price of this quality is lower than the reservation price of this consumer I. And this reservation price of the consumer depends on the product quality C. Okay, so it buys exactly 1 unit as long as the price it has to pay or she has to pay is lower than her reservation price R, and the reservation price is affected by the product quality, meaning that higher product quality increases the reservation price. And if we assume that consumers vary or heterogeneous in the reservation prices, just assume some uniform distribution, then we can put aggregate demand in a standard kind of inverse demand function, a standard kind of demand curve, where demand depends, of course, on the quantity, but also on the quality level. Okay, and an increase in product quality increases demand. That's what we assume. And just to illustrate that here, I jump forward a few slides here. Begin with a particular demand curve for a certain quality Z1 or C1, and suppose here what this just means is we have this number of different consumers. Each one has a different willingness to pay, and we have one with a high willingness to pay. We have ones with lower willingness to pay, as with a standard product as well. Later on, I will just give you some, in a sense, micro foundation of this demand curve. So the point is, if we have some price P1 and product quality C1, then all consumers with reservation prices greater than P1 will buy the good. Okay, should be clear. So at the price P1, we sell Q1 unit. What is interesting is that this consumer located here at Q1 is what is called the marginal consumer. These other consumers located at a index strictly smaller than Q1 are called the inframarginal consumers. Okay, and what is interesting is here is how such an increase in quality increases the willingness to pay of the inframarginal consumers compared to that of the marginal consumers. Okay, so the question is, suppose we increase quality level C1. How would that change our demand curve? Typically, what we assume, standard case, and that's what I just told you about the rich, in quotation marks, is that if we increase the quality of a restaurant, for instance, people with a high income will have or will experience a stronger increase in their willingness to pay than people with a low income. Okay, it's the same for newspapers. It might be the same for cars, for instance, okay? Higher willingness to pay for additional gimmicks, okay? For additional kind of equipment. And if we have this like here, what this means is that I can sell now, of course, the same quantity. If I increase the quality, I can sell the same quantity at a higher price. What is if the willingness to pay of the marginal consumers increases by more than that of the inframarginal consumers? This would lead to an outward rotation in this point here of the demand curve. That would mean the willingness to pay of the marginal consumer here increases by more than that of the inframarginal consumers. The poor ones experience a stronger increase in their willingness to pay. Okay. Once again, of course, that would mean that you can sell the same output at a higher quality, the same output at a higher price given due to your higher quality. But actually, under what circumstance would we expect that? So I would try to give you an example here. Jean-Tirol's example in his textbook is that we have a concert hall where you bought a ticket for your concert or for your opera, and this concert hall distributes some booklets with explanations and libretti. And Tirol says poor people have a higher willingness to pay or experience a higher willingness to pay because they don't have this Wagner libretto anyway at home. Okay, they do not own that or cannot afford a separate book on music or something like that. I never considered this very telling. My example is, think of the Toyota Corolla or another smaller or subcompact car, or say the Fiat 500. Okay, so the Fiat 500 in Italy, all rich people also have a Fiat 500 with which they go to the city. It's their second car because they have a big Mercedes in their garage, and if they go for far distance travels, they always take the Mercedes. But to go into the city, to go through these narrow streets and so on, they take the Fiat 500. But they actually don't care for whether this Fiat 500 has a very good old Fahrgestell. I even looked it up, undercarriage, or whether this Fiat 500 has air condition, okay, because they use it for trips of 1 or 2 or 3 kilometers only anyway, okay. Whereas for poor people, this Fiat 500 will be the only car. So for them, it's really important whether it has a good undercarriage, because if you travel for 300 kilometers, it will be a rather exhausting trip if you have a very bad Fahrgestell undercarriage, okay? So the idea is here, for these kind of products, where it's for the rich one in a sense a second car, but for the poor one's only car, we might see exactly this kind of feature. And these distinctions will be below once we look into the welfare effect, okay? Now, given that the monopolist now must choose both price and quantity, price and quality, we have two profit maximizing rules. First of all, as always, marginal revenue equals marginal cost in terms of the output for a given quality, but also we have a second optimization rule or maximization rule where we equate the marginal revenue from increased quality, higher willingness to pay. We also have an increased cost of higher quality for a given quantity, so marginal cost. And this I want to, if you give me another 5 minutes, I want to illustrate by a simple example. Suppose here our demand function, or inverse demand function, our demand curve is just this P is C times theta minus Q, and C is just an index of quality. And this demand function, for instance, results if you have a continuum of consumers I distributed over the interval from 0 to theta, and the indirect utility of the consumer is just this VI is equal to I C minus P, because then you know the indifferent customer is the one for which VI is equal to 0, and this means that means that we have EI C is equal to P, and what we know then, of course, is that this indifferent customer is determined by C, other way around, by P over C. But how many consumers do we have? Now, if these consumers are located in an interval from 0 to theta, everyone who has a higher index here of I, that is, will have a positive utility then. So everyone between, so Q will be just everyone from theta to I, okay? And if that's everyone from theta to I, we know that Q is simply theta minus P over C. And if we rearrange that, we come up with this inverse demand function. Okay, that's what we have. Here you see uniformly distributed. Simply each consumer has this indirect utility function, very similar to our above function. And we obtain a very nice inverse demand function. And again, what we have here is exactly this here. So these theta on the one hand together with C determines your maximum willingness to pay. On the other hand, the theta is always the total number of consumers. Okay? Given that we have a uniform distribution from 0 up to theta and a density 1. Of course, we also could change the density. If the density is 2, we would have 2 theta here, but that doesn't matter here. And again, the question, how does increased quality affect demand? That's straightforward. We have this case in which the inframarginal consumer gain more than the marginal consumer. Now, given, and we are almost back to our previous case, given to our question in the WebEx, given we have here our demand function, it's straightforward to set up the profit function. Assume for simplicity that the output costs are 0, like it's something like software, okay? And assume that we have some fixed cost of product development of quality. So if we want to have a better software, see these software costs increase more than proportionally. And yeah, that means that quality is costly and becomes increasingly costly. And now the marginal cost of quality are written down here as well, would be just 2 alpha C. And the firm's profit function is then simply price times quantity, revenue, minus here this quality cost. And here we substituted that, and now it's really straightforward and almost trivial. Just this is a standard profit maximization problem. We maximize that by choosing Q and Z. Okay, maximize that, and we get 2 first order conditions and solve for Q and Z. Okay. Here in the slides, and that's what you should do at home and check it, what I did here. In the slides, we do it like it was suggested just in a chat. We just, if you maximize profit and look into the quantity choice, we just set marginal revenue equal to marginal cost. Marginal revenue is just the derivative of this expression here with respect to Q, which is simply Z times theta minus 2 Z or C Q. And again, if we have this here, our diagram, you'll see simply marginal revenue, given that we assume marginal cost of 0. Remember, in both cases, irrespective of quality, we always get the same output. The same output, which is simply here theta over 2, but of course, we get different prices. One time we get this price, the next time we get this price here. Okay? And again, I jump back. So that's already what we already did, is we determined the optimal output. Q is equal to theta over 2. And next thing that of course determines also the optimal price, which I just already illustrated. It would be just Z times theta over 2. Remember here, this is our maximum willingness to pay. This is nothing else than our A plus the C. C was 0, so it's A plus C over 2, as always, okay? You always can check that. Yeah. So we have already determined the optimal price. What we do then is, what about quality? I have to erase it again. I have to erase it again here. So, and now you see here, when quality is set to, you get a higher price, and of course, you get a profit from increasing your quality. And I now have to jump here. Which was it, the last thing? It's here. And so the total revenue is just this here, marginal revenue from increased quality. Again, it's much easier if you just take the two the derivatives with respect to quality and quantity, get the two first order conditions and solve it. But here the marginal revenue with respect to quality is this sigma theta squared over 4. Marginal cost of quality is what we already derived up there, 2 alpha times z. Equalizing that or equating that, we get the optimal quality level. Okay, we get some optimal quality level, theta over 8 alpha. And on what does it depend? It depends on the number of consumers, theta, and of course our theta was in a sense two-sided. It also determined the willingness to pay for quality. So higher willingness to pay for quality and more people means higher quality level. First of all, here our monopolist invests in quality. Okay, that's an important result here. So our monopolist invests in quality, but given that I run out of time anyway, you will have to wait for the answer whether this quality level is too high or too low compared to what a social planner would do, or what would maximize social welfare or total surplus. We will only look into that next week. Okay, so I stop here. I will be available for some more discussion in WebEx. I thank you for your attention, and hopefully you'll be back next week. See you. Bye.